Okay, so before I start today, does anybody have any questions about the class at all? As far as what we went over the last few weeks, your paper that's due, I think the 11th, your term project that's due in a few weeks, any lotto numbers. So Chris is not feeling well, so I'm going to take over the second to last lecture. Next week, was it next week or is it in 2 weeks? I forgot. Next week, yeah, Tuesday? Yeah, Thursday. For the exam 3 review? Okay. I thought next week, Thursday, we were doing the for us to do the term project. We're meeting Thursday. I was thinking when we were doing exam 3 review. I could look it up, but look it up. It could have been. Okay, cool. Thank you. For a second, I was like, I can't remember when we were supposed to have it. But next week on the 18th, Ruth, myself, and I think Olivia will be here. If you're still working on your term project, you have ideas you want to run by us, you finished it and you just want us to take a quick look at it. We can't grade it for you right then and there, but heck, if you've got it done, we'll take a look at it and we'll be like, this is great, or fix this one tiny thing, it's even better, stuff like that. So feel free to stop by. We'll be here from 2 to 3:15 next Thursday. So today, second to last lecture, we're learning about kind of, as it says, the neural mechanisms of body movement, of control. You may have already taken the motor learning class. You might have kind of dipped your toes into kind of the neural aspects of movement. This lecture is it's not too long. We'll probably get out of here a little bit early, but there are some really good exam questions from this lecture. If you don't understand something, I have a habit, I get excited and start talking fast. If you want me to slow down, just say, hey, slow down, or can you go over that again? None of this is too detailed, so I'm not expecting you to be able to give me the biology of everything. It's just mostly very, very broad topics. The slides I'm going to use, they're just a little bit different than the ones on Canvas, just because I went through it this morning and felt I should add a couple pictures just to kind of clarify a few things. They're really, really simple pictures. If you want, I can send you the one I'm using, but once again, it's like 3 pictures. So essentially, when we move through the world, our muscles contract, they move our limbs, they move our bones through tendons. But the idea of movement, or the impetus, the action, is coming from our nervous system. Muscles, despite what people think, do not have memory. Muscles are actually quite stupid. They get electrical signals from your brain and are told to contract, relax, contract and hold, contract and release. Muscles don't have a say, they don't have memory, they don't choose to do things. That's the nervous system. So for us to do complex movement, our brain is on all the time. You do not use only 10% of your brain. You use every last cell in your brain. Your brain does many things you're not aware of. It controls your breathing, makes sure your heart keeps beating, tells other organs in your body to secrete hormones, other chemicals to keep you living. It controls when your eyes focus, when your pupils dilate. So your brain is always moving. Hopefully, we're all mammals here. So we produce body heat to keep us warm. We need calories, we need to eat food to keep us warm. Even that, the brain uses 20% of all the oxygen you breathe in. It uses roughly 1/4 of all the energy your body produces from food. It's always on. You don't use your brain is on all the time, and it likes to have lots of oxygen, lots of glucose, and it likes to be at a very, very particular temperature as well. So the nervous system is important. Unless, of course, you're studying EEG, what I'm trying to do, and you learn that you're just measuring scalpel activity in the brain might just be a big lump in your head. But so it says people who look at EEG, but essentially your brain is doing all of this. From simple movements to just moving through a crowd. You have to constantly calculate the trajectory of everybody else in a crowd, so you're not just all bumping into each other. So, like I said, we're going over very broad strokes today. But essentially, the nervous system is composed of two parts. We have the central nervous system, which is your brain and spinal cord, and your peripheral nervous system. These are the nerves and axons that are branching off from your spinal cord into your limbs, into more of your axial trunk. I say axial, I don't know if we've gone over that word, but axial is away from midline. So this would be your midline, axial away from your midline. So into your respiratory muscles, abdominal musculature, those muscles there into your limbs and like that. That's the peripheral nervous system. And this is composed mostly of nerves that carry info to and away from your brain and spinal cord. Signals that are going to your spinal cord are called afferent. And if they're carrying it away, efferent. Good way to memorize that. Efferent starts with an E. Exit starts with an E. They're exiting from whatever is being sensed, whether it's muscle tension, whether it's you accidentally touching something that's hot, getting stung by a bee. We see efferent information going from essentially your limbs, because we're looking at biomechanics, so that's what we care about at the moment. Going from the sensors in your skin, muscle, everything like that, through the peripheral nervous system to the spinal cord, up the spinal cord to the brain, where that information broadly gets interpreted. And then that information is then passed back through the spinal cord to the peripheral, to your muscles to tell you, take your hand off the stove. Hopefully, somewhere in that learning that the stove is hot is trained in your brain. So I kind of went a little bit further, but when we look at the transmission of information from our central nervous system to our peripheral nervous system, in our brain, this is a laser, but I can never see it correctly. Brain, spinal cord, and then this is just kind of a blow up your spinal cord right here. And we have our white matter, gray matter. You don't need to know too much of the difference from there, but we have our ascending pathways. So we see signals being, lack of a better word, grabbed from the external environment, whether it's pain, cold, heat, whatever, or muscle tension coming from the musculature into the spinal cord and going up the ascending pathway. So this is our afferent or our efferent system, or sorry, afferent system, sorry, broke my own rule there. Going into the brain, being interpreted in so many words, and an action is defined. It goes down the descending or motor pathway back into the spinal cord where an action is performed. So one thing though is not all nerve impulses make it to the brain. Easy way of looking at this, reflexes. When you touch something hot, when you go to the doctor and they do the knee tap with the hammer, your reaction to those is so quick, they would not actually make it to the brain and back. These impulses travel at the speed of light, but the speed of light is still a speed. It still takes time to do stuff. So what happens is we get something called a reflex of it. This is, we see something happen. Something happened, let's say you were at the doctor, he striked your knee with the hammer. Struck right at the patella tendon. right here that stretches that tendon and causes your leg to stick out. You see a receptor, and it goes to a sensory neuron in the spinal cord. And rather than go up the ascending pathway, it synapses. When I say synapse, basically means it's connecting and it's making a connection to another neuron. We simply, for simplicity, we'll call it an interneuron. So you have a sensory neuron synapsing with an interneuron. And the interneuron then synapses with a motor neuron. Your sensory neuron is carrying information about the sense or state of whatever was just experienced. The interneuron is simply acting almost like a relay switch. It's either on or off, on or off. So the sensory neuron synapses with the interneuron that's hopefully on. And then this interneuron then passes that information and we'll say the idea of the appropriate action to the motor neuron. Instead of going all the way up, right here, synapse is right here, and then immediately gets kicked back out of the spinal cord, and your leg goes like this. Or once again, if you're touching the hot stove, you immediately draw it away from the hot stove. If you were stung by a bee, take your hand away and scream like a little kid. So happens. So that's what we look at as a reflex. Every other movement that we care about, especially in biomechanics, is these ascending and descending pathways. We look at kind of normal motor control. This is what we're looking at. However, we do see if you were, let's say you are a trained athlete, we do this is where the kind of the motor memory myth comes from, is we're not necessarily looking at your muscles remembering what to do, but not only are these pathways become more efficient, it takes less time for you to do them. We can look at, and this is where you start going into motor learning and control. If you've already taken this class or will be taking it in the future, is we start looking at the training of reflexes or the detraining of reflexes. If you played Little League as a kid, when the ball got hit really, really hard and was screaming at your head and you were only 8 years old, you may have kind of covered your face with the mitt or tried to dodge the ball, and you had to learn to almost detrain that reflex and put your mitt in front of your face or in front of the ball rather than getting essentially spooked by the baseball. So when we look at the central nervous system, we're looking at the brain. This is the simplified version of the brain. We have our cerebrum, our cerebellum, our brainstem, and then you never say it, diencephalon. Sorry for my bad pronunciation. I never say that word correctly. What we're concerned for this class for movement is the cerebellum and cerebrum. So generally, when we look at the cerebrum, we're looking at the cerebral cortex. This is also an extremely simplified way of looking at the brain, that there are very designated separate areas of the brain that they only do one thing, they never talk to each other or anything like that. That couldn't be farther from the truth. To this day, if you were to ask any neuroscience person or neurologist, hey, is it really that simple? They would look at you like, well, if they were up on their science, they'd say no. All parts of the brain constantly talk to each other in a very, very efficient and subtle manner, one way or another. But for us, we only care, for this class, we only care about a few areas, and we'll consider these to be somewhat separate. And also, this is whether Broca's area for motor speech is weird, whether it's a real thing. But in the cerebral cortex, we have a few things we care about. We care about our sensory areas, our primary somatosensory area. This is where we start receiving this information, our sensory information from the bee sting, muscle tension, putting our plant in a hot plate again. And then the secondary somatosensory area, which we take this sensory information and that is interpreted, making sense of this. We haven't yet begun to come up with an action, a motor plan for what will occur, but we're interpreting this information. And this sensory information, we'll get into it a little bit later, is coming from essentially your five senses. You know, vision, taste, smell, hearing, and then another one we'll learn about is our proprioception, or sense of space. So, or we could say touch. And then we have some secondary ones as well. We have our visual areas, our primary and secondary visual areas. I'll get a little bit deeper into that in just a moment. Essentially, we'll assume that this brain has eyes. They're right around here. Light goes into the cornea of your eye, is passed through your retina, crosses in your brain, goes to your occipital lobe in the back of your head, and that information is sent to the visual cortices of your brain. And once again, that sensory information is received, then integrated and interpreted so that you understand what you're looking at. Then after the sensory information is received, it's interpreted. This is where we start seeing the idea that a plan of action is going to be passed to another part of the brain. These are our motor areas. So we have our primary motor cortex. If you look at the literature, if you were to go start looking into any sort of motor control literature, or even kind of neuroscience literature, you'll also see it'll be capital M1, which is another way they'll say primary motor cortex. Sometimes they won't even do the primary motor cortex parentheses M1, they'll just say M1 and assume that you know what they're talking about. And then the premotor cortex. So our primary motor cortex is generally assumed to govern kind of our more precise movements. So much like we haven't gone over in this class that much, but if you go into kind of, I guess, more clinical or anatomical kinesiology, you look at your gross movements and your precise movements. And you could look at the different types of fibers in there that are more or less in charge of those movements. But our primary primary motor cortex, is in charge of precise motor control. And our premotor cortex is responsible for organizing, coordinating those movements. So we're looking at our visual or our sensory information going to the premotor cortex, where it's organizing and coordinating it, sending it to the primary motor cortex for that action to be basically performed, to send it back down to the spinal cord and to your peripheral nervous system. And what often happens, you don't need to know too much about this, but that information is then sent to the cerebellum, where it's interpreted for errors, ways to improve, and it's sent back up through here, and it's constantly going back, up and down, up and down, up and down at the speed of light. So it's constantly monitoring your movement. So if you start making errors, it'll slowly start correcting your errors. Then we have our association areas. This is a prefrontal cortex. In this slide, we're looking at our cognitive functions, our emotional reactions. But when we look at kind of association areas, these are all often parts that are associated with the motor cortex, or associated with the primary motor cortex. They act as accessories to that cortex. They help with better integration. They help with better interpretation of these sensory signals. The prefrontal cortex, when it says cognitive function and emotional reactions, is where, I guess if you took like first year psychology, you hear about like Phineas Gage that had by the way, that's a myth. He was always kind of a jerk, If people didn't start paying attention until you had a railroad tie in his head. The legend is he was always kind of a jerk, but when that happened, all of a sudden, all the neuroscientists of the 1800s said, oh, this must be where emotions are stored. And they were kind of right. But the true story is Phineas Gage was always kind of a jerk. The railroad tie didn't change much. So we have all this information going through our brain. So how do we successfully move through the environment? How is this information detected? Let's look at the detection. We receive constant information through 5 primary senses. We have vision, your eyes, proprioception. We'll get into that, but that's where we're looking at our muscle tension, stretch of our muscles. It helps determine if we close our eyes, we can still locate our nose. Close your eyes, touch your nose, because we understand where our limbs and body are in space. And then the other 3, auditory, olfactory, and taste. Obviously, it's very hard for you to control movement and navigate the world through smell and taste. Sure, it's possible, but unless you're a canine or something like that, it's a little bit harder to taste guide you. So what we're concerned with as humans is our vision, proprioception, and we'll talk a little bit about auditory. Not much, because when we look at auditory, we start looking at the ears. We look at the inner ears. We look at inner ears are responsible for a more vestibular function, not necessarily for hearing. We look at movement. So vision. Vision detects, obviously. Light goes into the cornea, through the retinal nerve, crosses over, goes into that occipital lobe. You now see what's in front of you. You get the backwards image that's flipped upside down, and your brain interprets. This is information from outside the body, called an exteroceptive. This is giving you information about the environment around you. Lets you know how close am I to this table? How close am I to the door? So when I'm walking to the door, you might not realize it. You also think, I'm getting this close, I should probably start raising my hand to reach the hand. The other main sense is proprioception. This is information from inside the body. This is our body's position and movement. Once again, you can have your eyes closed and you can still touch your nose. You can be standing next to somebody and not necessarily be able to see them, but you have an idea of the relationship or how close you are. You're standing next to a wall and you kind of have an idea where your arm's length would be if you could actually touch that wall. Okay, so vision. For humans, vision is our most dominant sense, and it can override other senses. So, a good way to look at this is, yes, studies have been done to help understand this. One of the kind of common studies is, in VR, this person doesn't know there's a ledge there, never would, but they'll get their toes close to that, and all of a sudden, they'll start to detect that there is a ledge there. Good way of looking at this too is if you're ever at a stoplight or parked in somewhere, you're sitting in your car and the car next to you starts moving forward, you get just a little bit dizzy just for a quick second, thinking that you're rolling backwards. That is where your proprioceptive or your vision is being overridden by other senses. So you start to feel a little dizzy just for that second until you realize you sort of panic braking for no reason because you think you're going backwards. So here is a fun fact. Our vision, we have our eyes in the front of our face, right? Most of us have 2 eyes in the front of our face. Deer, like the deer in the headlights, they just stand there because they don't move or whatever. There's a reason for that. Deer don't have, deer do not have depth perception like we do. We have eyes in the front of our face, so we get two different angles. So if I'm looking at you, I'm getting one angle from my right eye, one angle from my left eye. They converge, and through neuroscience that I'm still struggling to understand, my brain calculates the difference in those angles, so I have depth perception. Deer, other animals, their eyes are closer to the side of their head, so they don't really see all of you with both eyes. They see half of you here, half of you here, and they interpret the whole body, but they can't really detect how far you are. They're very good at sensing movement, but not where that movement is headed or how far that is. So once again, it's kind of, deer in a headlights. It just sees that light. It doesn't know that it's actually getting closer. You're sitting trying to figure out, why is it all of a sudden so bright? What is that light? And then hopefully you stop at time or swerve off the road or something like that. So back to vision. Light photons enter the eye and stimulate the photoreceptors of your cornea. This is from your rods and cones. Your rods are kind of the traditional, like kind of black and white information that we see in dim light, usually black, white, and red, like a deep red. And then our cones are more sensitive to our brighter light. This helps with kind of us being able to distinguish colors and the sharpness of stuff. What's important to us, this picture isn't in the slide. Neither is the picture of the deer. If you really want the picture of the deer, I'll send it to you. But this isn't in there. You don't need to know everything about this picture. This, I just think it helps tell the story a bit, is we get light through our eye. It's passed down through our cornea into our primary visual motor cortex. This is where we see kind of an action from this. We see this information is then split into two pathways. Depending on which book you read or which study or paper you're reading or who you're talking to, they'll either say the dorsal or posterior or ventral, meaning anterior, depending on who you're talking to. I use anterior, posterior pathways. These pathways are distinctly responsible for this information. Your dorsal or posterior pathway, arising from your primary visual cortex, works to understand where the object you're looking at is. Where is it? And kind of deals with the kind of the motor planning. You're able to detect, well, it's about, in my brain, it's about this big, this close to it. If I wanted to walk towards it and keep walking away from it, I have to look to the left, to the right. Somebody's coming at me. Hopefully, we don't do like the weird Canadian standoff thing where I go right, they go right. Do this weird little shuffle down the hallway. But that is the posterior or dorsal pathway. That's where am I? How do I keep moving? How do I get through this obstacle? And then we have our anterior or ventral pathway. This is simply the what. What am I looking at? How big is it? What color is the t-shirt? Is that snake poisonous because its stripes are in a different order? Everything like it doesn't know if it's poisonous. But is it simply detecting of color, shape, a little bit of protrusions from it? So being able to detect what the actual obstacle is. So, oh, I forgot to boot up this video, or did I? But when we look at visions in sports performance, we're looking at putting. It's you being able to detect where the ball is, where the hole is, and then the how or what is, if I hit this ball, what is the likely path for it to roll? If you're at kind of a slanted green, it's going to roll towards the right. If it's slanted to the right, left, it'll roll to the left. So you develop a motor plan. how to get the ball into the puck. Same thing with free throws is you become aware of the average distance to the basket, the appropriate arc for your arm to release the ball at, so that it hopefully follows that arc and either hits the backboard and goes in the hoop or just goes into the hoop. This is the idea of quiet eye, that your eye is always taking in this information and helping with motor programming. You're not necessarily aware this is happening, but this is what is going on. And I want to boot this video up. It looks like I forgot, so I'm going to copy it right now and put it in this group. Dr. Ray wanted you guys to watch it. It's only like 10 minutes. It's actually a pretty good video. After the inevitable into that, so yeah. I'm going to say genes.
Attention, I dismissed it. Sure. The first time I experienced the yips, it was a pot, and I wasn't paying attention.
Yips. What some athleticians will talk about or athletes will talk about eating the yips. This is a repetitive mistake. Is you start thinking a little bit too closely about the action you're trying to perform, and you almost kind of choke or you decrease your performance because you're almost actively thinking about it too much, and better become a more natural progression. Guess I don't know if anybody's aware of this too. It's kind of a nice analog to this is people on a plane all of a sudden realizing they're on an airplane 3,000 miles an hour. This isn't right, sort of thing. Not the yips, but kind of the same sort of idea.
And I dismissed it. And then I obsessed over it the next day. Like I was afraid to hit those putts. I felt all this like tension and anxiety just come up through my arms, into my shoulders, my jaw.
Athletes can choke in every sport, but the phenomenon is so common in golf that it has a nickname, the yips.
It kind of makes your body really stiff and rigid. Your eyes get quick. It's hard to focus. You're thinking about the wrong things, and your body just reacts, and you miss the putt.
Elena Sharp is a professional golfer competing in her second Olympics this year.
The biggest issue that I had was probably in 2010. It was like consuming my thoughts off the golf course. I wasn't having fun in life in general, and I really felt like my career was over. And then it happened again in 2018, and I was thinking about, oh, I need to make this, and I just missed it.
That's when she learned about something called the quiet eye, which is defined as the final fixation or tracking gaze on a specific object before a critical phase of the movement. In golf, the last thing you see before putting is the back of the ball. In basketball, the last thing you see before shooting is the hoop. In shooting sports is the target. Researchers still don't know exactly how quiet eye works, but they found that training it can help people focus when it matters. Everyone from pilots to dancers to even young children.
It's almost like your mind's so busy on quiet eye. You have no time or no other space to think about other things in your mind. This is my 15th year on tour, and it's hard to believe that it's already been 15 years.
Alina and her wife, Sarah Bowman, live near Phoenix, Arizona with their 2 golden doodles. Sarah is also Alina's caddy, a job she started about a month into their relationship.
We joke we had a 3-week plan. I try it for 3 weeks. We both try it for 3 weeks. See if it worked. It did. So she had been struggling, and a lot of it did really revolve around her putting. And before the year even started, she said, you know, if I just really struggle again this year, I might just retire.
everybody goes through mental battles at some point in their career or even in a round as the day goes on. Especially when it counted, like to make the cut, you know, a putt, this would scare the hell out of me.
So Elena's coach put her in touch with Joan Vickers, a neuromotor psychologist based in Calgary.
We don't know what causes the yips. No one really knows, but I have a bit of an idea that people who experience the yips in golf, putting in particular, they have a very rigid routine that they go through over and over and over again. And I think they just wear it out. Basically, those neurons just become overloaded.
Vickers introduced Elena to Quiet Eye, the training technique she developed.
For Quiet Eye, I always line my ball up with the line facing like my target, where I want the ball to start, and then I have my bullseye on the back of the ball, and then I look at the bullseye, and then I stroke, and it's like I can see that bullseye still, and then I look up. If it's the right line, it goes in.
Quiet Eye actually came from Vickers' own experience playing sports in college.
In basketball, I was a good player, meaning I scored maybe 10, 12 points in a game. All of a sudden, in one game, I scored 27. I shouldn't have been able to do that, but something happened. Something was going on that I didn't understand.
But she did have a hunch that these hot streaks were vision-based. Humans can only see a tiny portion of our visual field in high resolution. It's an area at the center of your gaze, about the size of your thumbnail viewed at arm's length. This is called foveal vision, named after the fovea, a depression in the eye's retina. Everything that's blurred around it is peripheral vision. Skilled performers need to be able to make quick decisions based on foveal vision. So Vickers decided to study it with eye trackers as athletes focused on their target. She found that expert golfers tend to fixate on their final target earlier and hold that fixation longer than people with less experience, resulting in a quiet eye of up to 3 seconds.
Here, this is his quiet eye. Notice he's centered on the very back of the ball, and he doesn't move to take a look to see where the ball is actually going until it's about a couple of feet in front of him. That's the hardest part, because people get so anxious and they want to see where the ball is going that they look up, and when they look up, they actually move the club head.
Novices, meanwhile, fixate on the ball for less time.
They're just trying to figure out, how do I hold the club? Where's the ball? What am I aiming at? How do I make this swing? And they're just totally overwhelmed. And their eye movements reflect the mental chaos that they're feeling.
Vickers started teaching athletes to develop their quiet eye as a way to build focus and avoid choking, and the results have been remarkable. She trained a university basketball team on quiet eye for 2 league seasons, and the accuracy of their free throws improved significantly more than the 2 control teams. They actually ended up with a better shooting percentage than the NBA average for the 1999-2000 season. Over the last few decades, researchers have replicated Vickers' findings in many other high-skilled activities. The technology has also evolved.
The eye tracking technology uses a series of cameras that are mounted around the eye, and they sense infrared light, which is sent into the eye and reflects from the eyeball and different parts of the eye. And this allows us to understand essentially what angle the eye is pointing at relative to the head.
Sam Fine works with athletes on their quiet eye. Many of them perform in the modern pentathlon, which is a sport that involves swimming, fencing, horse riding, running, and finally shooting. That's where the quiet eye comes into play.
It's this wonderful, terrible mix of physical fatigue, psychological pressure, and the final event in the series of 5 events. So it's this cocktail of things that can either go wonderfully well or terribly wrong.
Before the pandemic, Fine was working with Georgina Mitchell, a pentathlete who hopes to compete in the Olympics someday.
So it was mostly like I lacked quite a lot of consistency, and at like big competitions, I would shoot really badly because I'd be nervous that I'd not be thinking about the process or anything. Sam said to imagine like the bubble blowing up, so it gets bigger as you get closer to squeezing the shot. And that just helps me to concentrate on the sights without worrying about anything else.
Researchers are still investigating how this actually works in the brain. But past studies suggest that quiet eye may be correlated with suppressed activity in certain brain regions that can compete with focused attention.
So as you become skillful at any kind of aiming skill, you are naturally refining the way in which you control your eyes to feed information to your brain in a more efficient way. Quiet eye training is a step further. It's about making people consciously aware of what they're doing and enabling them to adopt strategies that allow them to repeat that again and again.
This doesn't just apply to sports. Quiet eye is an asset for anyone whose job requires precise motor skills, like surgeons. The principles behind it may be useful for everyone.
The obvious application that I use, I think, on a daily basis is teaching my young children how to perform basic everyday household skills, right? So brushing their teeth, maneuvering their cup of milk from one work surface to another. And that's really liberating for a child to have a simple instruction about keeping their eye on the ball and not focusing on the complicated mechanics of where they stand and how they position their body.
Why that leads to consistency. It just takes some reps and intentional focus on what you're doing.
I would say she's a lot calmer. And there is a quiet confidence about her that she, I don't think, had before. While you still are going to always have your storms and your roller coasters and hang around, I would say our roller coasters, our ups and downs, are a lot milder. Kind of on the kiddie roller coasters, you know?
So that was quiet. One thing that was mentioned in that video towards the end is the golfer mentioned that if you use attentional focus, this is an area I am not super familiar with, though the lab I work out of, seems like half of in the lab I'm working out of uses attentional focus, so it's kind of funny, I still don't know much about it. But essentially attentional focus is how well are you looking at either the task itself or how you're paying attention to how your body is moving to accomplish that task. Generally, it seems that focusing more on the task and not necessarily, well, I need to put my foot here, do this, and I need to do this, and do this. Generally, just focusing on the task leads to better performance. Okay, so a little close to finishing. So other than vision, what are the other major sources of information? The next biggest one, proprioception. Proprioception is simply your sense of your body in space. Once again, this is close your eyes, touch your nose. Stand on one foot, how well do you balance? Can you count? Can you move your fingers and know which finger is curled and which is sticking up without having to look at it? So how does this differ from vision? It provides information from inside the body. None of this information is coming from outside the body. So we're looking at an interoceptor. So an exteroceptor, and interoceptor. So where does this information come from that's inside our body? Comes from essentially our muscles, but two specific parts of the musculotendinous unit. The musculotendinous unit is simply your muscle and your tendon. We call it the muscular tendinous unit, excuse me. So receptors in the muscle tendons, joints, and inner ear provide internal information about movement. There's two specific receptors we care about, our muscle spindles and our Golgi tendon organs. Our muscle spindles are within the actual muscle itself, and they detect tension within the muscle. Okay, if that tension, we're looking at that tension is greater, it might order, if we're looking at a reflex action, it might order the muscle to contract or relax. But it's simply all it is doing is detecting tension within the muscle. And it's sending this through an ascending pathway to our sensory organization centers in our brain and our motor centers within our brain as well. So we're able to, in so many words, approximate how flexed our elbow joint is, or how straight our leg is. The other receptor is the Golgi tendon organ, or our GTO. This is located within the tendon of the tendinous unit, excuse me. This detects tension within the tendon itself. So if we go back to going to a doctor and having them do the hammer tap on your knee, what they're tapping is the ligament from your biceps that goes over your patella into your tibia right here. This tendon right here, they're tapping that. That stretches the tendon in your leg at your knee joint. That tension is sensed by the Golgi tendon organ, and it causes the muscle to essentially spasm. The leg just kicks out. So that's our Golgi tendon organ reflex. That's our reflex arc. None of this information is going up to the brain for you to interpret, like, oh, I wonder what that hammer is for. What should I do? I wonder what's for lunch today, and then all the way back down to your leg. It's a reflex arc. So it's going from the sensory neuron to the integrative neuron to the back to the motor neuron. We also have sensors for our vestibular system. When I say vestibular system, we're mostly looking at balance. If you ever had an ear infection when you were younger and you had more fluid in one ear, you feel a little bit dizzy, you may have kind of lent to one side. That's because we see increased fluid on one part of your inner ear. Messes with your vestibular system a bit, so you start to feel heavier on one side. There's two integral parts to our vestibular system within our ear: the otolith organs and our semicircular canals. I reordered these incorrectly, but these are our otolith organs. Their main concern is linear acceleration: forward, backwards, up, down, left, right. Within these receptors, we see these air cells here, and then these crystals here, and they're simply suspended in like a gel type goo. When you move in a linear fashion, forward, backward, up, down, left, right, that gel is disturbed, and fluid kind of substance is disturbed. So it displaces the hair cells just a bit. These hair cells also have neuronal receptors in them. So it's detecting the movement of that hair. That's why you can close your eyes and still walk forward and know you're walking forward. You can close your eyes and bend down and pick something up. You still know that your head is going down. The other one is our semicircular canal, and this deals with our angular acceleration. So if I quickly turn my head like this, the same type of mechanism is occurring. We see our hair cells and what we call the cuticula right here. And when I rotate my head like this, that gel matrix is once again being disturbed and displaces these hair cells in such a way. We also have neuronal connections within them as well, that when they're displaced, they're signaling a neuron that goes to the sensory cortex, to the primary motor cortex. And so once again, you can understand that you're moving your head in a rotational manner, or your head is being displaced somewhere in rotational. You might not be moving your head, you could be on a tilted head. But your head is part of the system that's going rotating. So what if we lose one of our senses? either chronically or acutely. I tried to find a good long video. I wasn't going to make you watch the video, but there's a few out there. You do some Googling, but there is a man named Ian Waterman. Due to a virus when he was younger, he lost the sense of proprioception. There is one video he's telling a story about essentially he can't use his pockets. He can't put his hand in his pockets and grab something because he can't detect how his fingers are moving without looking at them. All the movement he can perform, he has to visually see his movement to understand it. So part of his rehabilitation is learning how to control activities using only visual control. His sense of touch is also diminished. So he could have his hand somewhere. He doesn't actually, without seeing his hand, it might as well not even be there. Might as well be across the room for all of these. This is similar to when a person goes blind, possibly later in life, through an accident. They have to relearn to control movement. They have to rely on these other systems. So when we look at kind of what we consider to be a healthy functioning nervous system, our lecture today is we have our visual information, our proprioceptive information, and a few other sensory informations, like I said, a little bit of smell. Hopefully you're not guiding your way back home by taste. But we'll still see some other input from our other sensory information. This leads to a successful movement. If somehow we take away the eyes, we take away vision, that's more than a third, because vision is, when I look at humans, our eyes are the primary visual system. That's where we get the majority of our information of our environment and our movement. So we take away vision, what happens? A really cool thing. The system will reorganize. It'll usually take for it to reorganize well enough for you to function optimally. It does take training and rehabilitation, but the system can reorganize and rely more on other sensory systems. The common trope is when somebody goes blind, their hearing gets better, or they can sense their movement better. But we look at almost a reweighting. So let's say we have our three sensory systems, our vision, proprioception, and then the other stuff. And we look at it's 40, 30, 30%. So 40, 30, 30. We get rid of that 40%. Our proprioceptive system, our sense of touch, then contributes more information, or the information that it is contributing is weighted higher in our central nervous system so that we can correct our movement or perform movements better. This happens in balance training all the time. Usually it doesn't take too long. The Nintendo Wii Balance board has been used and is still being used a lot for this. Simply, what's the best way to teach a skill is turning it into a video game. But simple as that is we see a reweighting of this information. We see it reweight to more proprioceptive and vestibular information away from vision because vision is no longer there. So we see those have a greater weight placed on them. So more information comes from those senses and is interpreted within the brain and used to perform a motor plan. So I think this is a little bit out of order, but I think Dr. Ray really doesn't like Shaq. It's brought him up a lot. But it is because they've used some sort of sensory deprivation to help Shaq with his free throws. Maybe he could use quiet eye. Consensus was he should have started shooting grinding style. But that didn't happen. Now he's like a third of the owner of Papa John's. Did all right for himself. So understanding the reorganization following sensory loss is really interesting. However, larger question is how each sensory system contributes to successful movement. In the lab I work out of, we have a really cool device. Sadly, I wasn't there to develop it, but we use smartphones. We put a smartphone application on these smartphones. All we're using is we are simply hijacking the accelerometers in the phone. So when you turn your phone to the side when you're watching YouTube, it gives you a landscape. Bring it up, it gives you portrait. We're using that's our accelerometers and gyroscopes in your phone. We're hijacking those. We place the phone against somebody's side and have them step in place for a while. Then we have them step in place with their eyes closed. Then we have them step in place while they're shaking their head back and forth like this. Each of these different conditions, we are either subtracting a sense or messing with one of these sensory systems because we are trying to determine if there's been an injury. Usually time we're looking at concussions or some sort of head trauma. If there has been an injury to the head or an injury to these sensory systems, which one has been affected? If we know, okay, well, they can step in place with their eyes open just fine. But as soon as they close their eyes, they can't, if their rhythm is all messed up, they barely lift up their legs anymore. They may be picking up their foot way too high and slamming it down because maybe we're looking at somehow the proprioceptive system has been injured in such a way. So to rehabilitate anything, you have to understand what was damaged first. So that's it. So we kept my promise. We're getting out like 20 minutes early. Does anybody have any questions? Well, Thursday. If you're still working on your, I'll send out another announcement. If you're working on your term project, you're stuck on your term project, stop by. You can also, you don't have to stop by too. If you want to email us, we can set up a Zoom invite. I can try to guide you in a term project over email, but after a while, I'm just typing out a novel. It might be easier just to have a conversation through Zoom. We have the Slack channel as well. You go through the announcement list. I put a little link in there for you to join it as well. If you don't have any questions, have a good one. Have a good rest of your week. And I hope this helped. Once again, Thursday the 18th, next Thursday, not this Thursday. Sorry if I confuse you, I'm really sorry. My brain, I'm working on a different calendar right now.